record, then share. Okay, now we're recording, I think. And you're all seeing my screen. So on the left, I have a terminal. And I suggest if you're following along and doing these steps on the computer as I go through the tutorial, I suggest you open a terminal as well as a browser next to it. And here my browser is already on the GitHub page for this SIG ATaCR session. And there's a bit of a description. We're all in the Python session, so you probably want to scroll down already to installing the Python version. I put a video here with the link, so it's probably too late if you haven't done it yet. But if you're wondering or failed to install it, go back there. Actually, I will reinstall everything in front of you so you actually know how to do it. The Git repository for the Python package documentation page with a link here. And so before we start, also, I'd like to point out that these codes are hosted. Currently, the Python versions of the code, obviously, Helen has her own Matlab version, and the ATaCR version in Python is really a carbon copy, well, almost, of the Matlab version. So I should give credit to Helen and other people that have contributed to the Matlab package. This is a Python implementation of the same code and based on all of these tried and true techniques that Helen talked about. So these codes are hosted on the NFSI. If you were there yesterday, I talked about the Canadian National Facility for Seismic Imaging. We have a GitHub page. So you see here a few packages that are present on this GitHub page. One of them is OBS tool. That's the one that we're going to be using. And there's another one, OrientPy. And if you find that you like these codes and you have a GitHub account, make sure to star those so that will increase the visibility of these codes so that other people can also see them. So just briefly, going to go into OrientPy. Helen talked a bit about this. About how to orient your horizontal components. So I implemented another Python package for this. I'm not going to explain any of it, but there is a documentation that accompanies this with a similar format to what we're going to do with OBS tools and the ATaCR package. So once you're familiar with OBS tools and you would like to go over OrientPy, you'll see it's very similar structure and similar way to run things. So I invite you to look at this code as well if you're interested in orienting your horizontal components. I opened the OBS tools page here on the GitHub repository. So this is where the code is hosted online on GitHub. There's a little bit of a description. You'll see there's a DOI here. If you click on this, it'll take you to a Zenodo archive with all of this code, and this is citable. So if you use the code, also consider citing it in your papers. And the way we're going to run this is going to go to the documentation page. Actually, I think it was opened already here. Let me go to the top. So this is the main way to find out any information about OBS tools. It has a table of content on the left. So GitHub repositories with the OBS tools. One of the packages will require for this tutorial, and the Matlab repository on GitHub as well. Some of the same references that Helen talked about. A license, just a disclaimer saying we're not responsible if you misuse this code and so on. And the installation. So this is very similar to what I did in the video, but I will redo it here for you. I'm going to follow the steps that are on this page.
Pascal, sorry to interrupt you. It seems like maybe your screen share is frozen.
Is it? Okay, let me stop sharing and I'll reshare. Do you see me going over like different pages of the browser? Yes or no?
I don't think so.
With this?
I'll record it from here on out.
Okay, perfect. I was saying this is the installation steps for installing the Python version of ATaCR. And I'm going to reinstall everything in front of you. It really doesn't take too much time if you have installed Conda ahead of time. So I'm not going to go through the Conda installation, and this tutorial is only guaranteed to work if you have installed everything with Conda. If not, there are risks of having conflicts between different package versions in your current Python installation. So if you have problems with the installation part, please leave this to the end and just sit back and follow along. But if you have installed Conda, I can guarantee that this is going to work. The first step when Conda is installed is to create this virtual environment. Just copy and paste these lines. And this is creating a new environment called MSS. It's installing Python 3.3 as well as OBS Pi. And so OBS tools is built around tools that are available from OBS Pi. And so we require installing OBS Pi. And therefore now I've created this environment where Python 3.8 and OBS Pi are installed. I need to activate it. So activate MSS, that's it. I'm now in this virtual environment, and all I need to do, and I'm not gonna clone the Git repository now. I'm just gonna install using the PyPy prepackaged version like this. And this is going to download all of the dependencies for OBS tools and the stdb package, pandas, as well as some other PyQt packages. And there you go. I have installed OBS tools, and I can check that this is the case if I import just OBS tools like this. We know now that this takes a little bit of time because it seems to be a large package, but it will install without any problem if it's installed under the Conda package distribution. And there we go, nothing happens, so we're happy, quit. So I have installed OBS tool on my computer. And you don't need to be in any particular folder to do this. I'm currently in my home folder, and you see my home folder is pretty boring. I have just the typical folders, and I did create this MSS folder for this tutorial. So this is where we're going to work from. And if you watch the tutorial, on the video on how to install, you see that I actually downloaded the OBS tools as well. I cloned it already. But it's already installed on the computer, so I don't need to do anything further. So now OBS tools is installed. I need to clone this SIG repository from GitHub, and I'm going to put it in that same folder, that MSS folder. So I'm going to clone this Git folder right now, and it's pretty fast. That's it. It's done. If I look into my folder, I have this SIG directory that's created, and inside this SIG directory is some more folders, data, events, the Matlab setup that we're not going to use, and the README file that's on GitHub. It's this actual README page here. So now I'm ready to start the demo. So we're going to go back, so not Orient Pi, but OBS tools, sorry. So OBS tools is installed, and we're in the right folder to start the tutorial. One more thing you'll notice, there's two modules in OBS tools. One of them is the ATaCR module that Helen described in the introduction. There is another module that's called comply, and this one is to actually calculate the compliance. So ATaCR calculates the compliance, but it uses it to correct for the vertical component, whereas this module just stores the compliance with some tilt corrections, if you'd like. And the compliance itself is useful, for example, to determine the velocity structure because it monitors the variations. It's a forcing in the Earth that you can use to look at the velocity structure. And there's documentation here. And if you go down, you'll see some figures that are produced by this compliance package, the coherence that Helen was talking about, and the compliance within a certain frequency band. I'm not going to go over this actually, but later on, if you're interested, you can look at that. So let's start this tutorial with the ATaCR package. There's some introduction here, so same references that Helen talked about. Definition of the noise corrections, just very simple text. And if you're a more advanced programmer, you want to use OBS tools in a sort of API fashion, you would look into this documentation here about how to use these different classes. We're not going to go over this today, but for example, if you were interested, there's also an example on how to use these different classes. There's container classes, utility functions, and so on. We are going to use ATaCR through command line scripts that we're going to call from the terminal. And there's 6 of them that are listed here. And if you just click on the first one, there's a helper page. So whenever you're stuck, you can go back to this page. And actually, when OBS Tools is installed, there's a helper page as well from the terminal. So you just copy this line here, and you can just copy it, paste it onto your terminal, and it's going to bring up this helper page, which is just this here is reproduced from the terminal. So you're going to see all of the different options. For example, how to use this command. So ATaCR download data with some options and a required input file. I'm going to go over what this is in a moment, but this indicates the types of options that are available to you when running this script. Some server settings, you can look at different archives like IRIS or INGV or other ones. You can pre-process the data when downloading and so on. There are time search settings. For this tutorial, we actually ran this command for you and stored the result into the folder called data. So if you go into data, there's one more folder with the station, and you see all the SAC files have been pre-compiled for you, and that was done using this ATaCR download data. I'm going to go back to this in a second. So this is where you would look for help on these scripts or on the terminal, typing that command -H. And if you want to know where these codes are installed on your computer, you type which ATaCR download data, and it's going to show you this is the path to where this script is installed. And you see it's installed under Anaconda, this MSS environment, under bin. This is where it's located currently. That's where we installed it using this virtual environment. So let's jump in with the tutorial. So there's several steps here. There's 6 steps that more or less correspond with the 6 scripts that I just listed. The very first step is to build your station database, so the information about the station you are using. There is already a limitation on this code that I want to point out, is that currently this uses only data that are stored on one of those archives, so either IRIS, INGV, or the other ones. So if you have private data, you're not going to be able to use some of these tools. But in the near future, this is going to be relaxed, and hopefully you can help contribute making that possible. But let's start with the first step, is creating this station database. So it is using this stdb package that I just briefly mentioned. And if you want to know more about this package, it's also on GitHub, and there is also a documentation page and how to create a database by querying the FDSN, how to create one from a comma-separated value file, how to merge, list, generate dataset, and so on. And just as a quick way to find out how to search for your station through this STDB package, GMAP website here is very useful. So for example, we're going to use the network 7D for Cascadia Initiative and M08A. And if you just update the map, it's going to show you where that station is. This is the one we're going to use for the tutorial. And you see it's on the shelf really close to the break towards the trench in southern, well, central southern Cascadia. So you see this is M08A. So really, this is not part of the OBS tools. It's just a nice tool for you to use when you're searching for stations that are available on these archives. So let's go back to the tutorial. First step is to create this database for station M08A. So the first step is to run this line. You run it inside of your SIG folder. So you make sure you're in the SIG ATaCR folder where all of these other folders are located. So you just copy and paste this line. What this is going to do, if you look here, so it's going to query the FDSN to create this STDB file. This is our in-house way to handle station database. Maybe also that can change in the future, but right now this is how it's set up. You're searching for a network code, 7D, a set of channels. Here's the question mark, H question mark. So it's going to try to find patterns that's available on IRIS. That has an H in the middle for the component name, and that refers to seismic data. So anything short period, long period, broadband, and any component. And then the name of the station. That's the input for the name of the station. And you give it the name of the file that you want. And in this case, I just gave it the same name as the station that I'm searching for. If you put this, it's going to put the output of your of the command on the terminal into a log file. But if you want to see what the code is doing, just ignore that log file line, and you see that failed. The reason is I'm using a Z shell or Z shell. You can see it here on the top of the terminal. Maybe it's a little bit small, but the Z shell does not like these question marks. So if you do have a Z shell, just put these quotes on each side of the question marks. This is mostly on newer systems. So it has run. So you see what happened here. It was searching for these parameters and it found one station. The output file is both in the CSV and a pickle file. And this is the information for that station. So if you look into your folder, there is now a CSV file with some station information and a pickle file, PKL. This is a sort of a format that can only be read by pickle, which is a package in Python. So you can't open this file, but you can open the CSV file and see what it contains, or just type M08 more, and you see that's the network code, station code, location code, components, start time, end time of the deployment, latitude, longitude, deployment depth. So it's negative because it's below sea level. I think this is polarity. It's the correct polarity, and this is the azimuth of the H1 component. Right now it's set to 0 because it doesn't know what that azimuth is. And it says open here, that's incorrect, that's a bug from the code, just ignore it, doesn't matter. So now we have our station database, and I'd just like to point out that we can actually have a different database. For example, if you ignore the -S and you want to look at all of the Cascadia initiative stations or all of the network code 7D, you would give it a different name, maybe CI, and let this run, and it's creating this ci.csv and ci.pickle. And there's a lot of stations in that folder, in that database. You see all of these stations. So this is how you would create a new database with different stations. But we're going to stick with just this one, M08. And you can see the content of this station file by listing the content through this ls.stdb.py script. And if you just type this, you see the station information. So some things are still buggy, like the status that says open here. Here it's incorrect. Okay, so net we really now start to go into the ATaCR steps. The first step is to download the noise data, and this is going to download day-long SAC files that are downloaded into this folder called data here. And you see there is another subfolder which has the station code and the station name, the network code and the station name. And if you look here, as I did, this is where all of the SAC files have been downloaded. But just one thing to keep in mind for this tutorial, I ran this line, but I added one option because otherwise the files would have been really large. By default, it's using a sampling rate of 5 Hertz when it's doing the pre-processing. So I ran this line with sampling rate equals 1 to downsample to 1 Hertz in order to put these files on GitHub and therefore not overload GitHub with large files. So if you want to rerun this, make sure you add this option here. Or if, and also if you already have this data set with the right folder structure, and if you just type this again, it's not going to do anything because it finds that all of the files already exist, so it doesn't continue. So if you want to overwrite these files, if you look back at the scripts helper page, there's an option to overwrite. So if you want to change this, this pre-processing steps, like change the sampling rate, or maybe you want to do the compliance in a different unit, these are available, or pre-filter for the instrument deconvolution on a different time search, you can do that. But make sure to overwrite if you want to crush that previous data set. So that has been done. So keep that in mind. We're using 1 Hertz data right now. The second step is to collect those daily averages that Helen talked about. And it's also doing a quality control step already on these data. It's gonna look at each day-long set of seismograms and pressure and determine the power spectra on each of these components. And it's going to do some quality control that Helen talked about. Like it's going to flag windows that are bad based on maybe some spurious signal that turns up in your data during that time window. So if you want to look at the page, the helper page for daily spectra, you see there's a bunch of options as well. And so I'll remind you that all of these scripts run using the input database file. And in that case, you notice I had this m08a.pickle. This is required for every script that you run. So the other options, some parameters that Helen talked about. So the size of the windows that you're looking at. There's always some default values. So a lot of times you don't even have to care about these, but you can look at different values if you'd like. So default, it's 7,200 seconds or 2 hours. The amount of overlap between windows over which it's going to calculate the power spectral properties. So now by default, it's 30%. The minimum number of windows that are required to be good to keep that within the daily average. to keep that day as a good estimate of a noise for that station. A frequency band over which to do these quality control steps. There's some default frequencies here, 0.004 hertz to 2 hertz. The tolerance level for the standard error times of tolerance. By default, it's 2 times standard deviation, I should say, probably. The alpha significance level for iteratively flagging windows that have been already pre-flagged, so 95% confidence is the default. Whether you want to use the raw data and raw spectra in that calculation to do the quality control, by default it's going to use a smoothed spectrum. And finally, whether you want to rotate or not the horizontal components to the direction of maximum tilt that Helen also talked about. By default, it calculates the rotation, but maybe you're not interested in that. But you're going to see that's not really important for the noise removal part. And you can produce intermediate figures for this step. So if we go back to the tutorial for daily spectral averages, really all you need to do right now is copy and paste this line here in that same. So if I kill this and I need to be in that SIG ATaCR folder, and I copy this line, and it's going to do this quality control step automatically. And then you see how many good windows have been flagged, and it's proceeding because there's more than 10 good windows. And the maximum here is 16 windows based on like the 2-hour long windows with 30% overlap. So that's if there's 16 good windows, it means that it's essentially all noise during that day. So it's doing all of this quality control step automatically. And then here we're not producing any figure, as you're noticing. So it has completed, and it actually has created a new folder called Spectra. So you can go into Spectra. It also has the same structure with the network code and station. And you see all of these new pickle files. So each one here corresponds to all of the spectra for all the components for each Julian day in March. So this is 1 month of data. I should have specified that. It's 1 month of data for that station. Now, if you wonder, like, how can I actually read these files if they're all pickled? You open a Python terminal, and you need to import pickle. And I'm going to rename it as PKL for brevity. And you can import, let's say, SP1, whatever you want to call it, pkl.load. And you need to open this file. So I'm going to select the first one, copy, paste this, and read binary, close everything. And this is reading this SP1. And you see it's a day noise object. If you want to look at what's inside this day noise object, you can print it as a dictionary. This is kind of advanced Python programming, but it just give you an idea of what these things contain. So there's the window, all of this information that we looked at in the options. The transfer function list, which is the list of the possible component combinations that you can work with to do the noise corrections. And if you wanted to just look at this variable, you could print sp1.tf list, for example, and it extracts just this one part of the variable. And you see now they're all true. So all of the components are available to us to do the component corrections. And there's the frequency array, and also the good windows. They have been flagged all as true, so they're all good, and some more variables in here. I don't want to spend too much time doing this, but this is how you would look at the content of these pickle files. So I'm going to go back to my SIG folder. And now I'd like to actually look at some figures. So let's rerun this. But instead of rerunning it for the entire data set that we have, I can specify a start and end time. So I'm looking at only one day on March 4th in 2012. And I'm specifying, plotting all of the QC figure and the average figure that's spit out at the end of the process. And to run this, I also need to overwrite whatever was present at the beginning, specify the station file. And I copied this, I think, and I just run this again. And you see it's producing the same figure that Helen showed with these pressure components, these pressure signals here that have been flagged as bad windows. And you can see there's going to be another one that's been flagged. So this is the same that Helen showed. There's another figure that's showing the windowed the averages for every window. So these are the power spectra for component H1, component H2, HZ, and HP. So this is the pressure. And you see these two windows for which the pressure component was bad. So they have been flagged as bad windows in red. And there's also another one that you kind of make out that was flagged as bad, presumably based on some of the seismic signals rather than the pressure. So you can save these figures if you like by saving them directly from the figure panel. And this is the average of all of the good versus bad windows. So the average of the bad windows doesn't make really any sense, but the average of the good windows is what you're going to work with in the corrections. And I'll note right now that these are the smoothed spectra, and we're not using the smoothed spectra when we're correcting. We're using the raw spectra. This is just for the quality control step. And if you want to save those figures, you can rerun this, but add a flag with save figure like this. And this is going to run really quickly, and there's not going to be any output produced because when you save the figure, it doesn't show them to the screen, but they're actually stored now in this folder. There's a new folder that created. It's called plots. If you go into plots, you have all of these figures that were just that popped up on the screen previously. We're not going to look at them. Just running quickly through this tutorial right now. I'm back to the main SIG folder. The next step is to produce some kind of average of all of these daily measurements. Because as Helen was saying, if you want a more stable correction, let's say you probably want to include more than one day of noise data to do the correction. So it's possible using this script. It's called ATaCR clean spectra. And by default, it's going to look at all of your daily spectra that are stored here that you can see still in the terminal. By default, if you don't specify anything, it's going to load all of these and produce one average. And it's going to do another quality control step, flagging the days that appear anomalous within this time range of daily spectra. So there's an additional quality control step. And you can also plot these quality control figures. So you can use all of the default. If you want to look at what these default options are, go back to this helper page. It's useful to use a start and end time if you want to look at, say, a week before an earthquake happened, for which you want to use the spectra to do the noise correction. So you can specify different time ranges before the earthquake to use those in the noise correction. Same kind of quality control options, frequency band, tolerance threshold, alpha parameter. I'm not going to go over this again. All of the different figures now that are produced, and you can also here have the save figure option, and you can save them in a different format if you'd like. So going back to the tutorial for this particular step, we're just going to run this quickly, just copy and paste again. So it's going to produce all of these figures, and and you'll see what happens. This is really quick now. It's flagging all of these good and bad windows and in good and bad days of the average daily spectra. So now it's flagging a lot of stuff because we're very restrictive with the tolerance and the significance levels. And you see even a single day had these anomalous pressure signal for the entire day, it seems. So these are now thrown away in this averaged spectrum for that particular time range. So these are the good and bad windows. These are showing just all of them. I don't think this is a very useful plot, but it's there anyways. And again, the average of all of the daily spectra for the good windows in black and the bad windows, the average of the bad windows is not really meaningful again, but it's there. And then also all of the different functions that Helen talked about, the coherence between 1 and 2, 1 and Z, 1 and P, 2 and Z, 2 and P, and Z and P. So all of the different combinations. And you can see the coherence for the bad windows is probably very low most of the time. And you see some weird takeoff of the coherence between Z and P. So I'm not spending much time here. Coherence, and you also have the admittance. And I'll note that the admittance of Z and P is actually the compliance signal that you can use to invert for shear wave velocity structure, for example. But it's still not noise-free. It still has some tilt noise in there. So you might want to remove that first. So the admittance between all of those components that are used to calculate our transfer functions later on, and the phase that Helen talked about. If you're interested, you see the phase between Z and P is really stable and close to 0. So they are in phase over this bandwidth, and that's why the coherence was so high. And the coherence between the horizontal 1 and horizontal 2 components, this is the tilt direction. It's the azimuth from H1. So there are obviously 2 directions because it's has this periodicity. And the phase of the coherence between H1 and H2. And you can use this to identify what is the maximum tilt direction. And you can further use that in the noise corrections later on if you'd like. And we'll see this is also done automatically in this code. So these are all the figures. Again, we didn't save them. We just popped them on screen. If you want to save them, you type this additional option, but it didn't run because it's saying, well, I found all these files. These already exist, so I'm not running it. So you just have to overwrite everything. And this is quick. And now you're going to see there's same kind of folder structure. Now it's taking time to create the figures, actually. Now it's done. And if you look into the content of this folder, there's a new folder that was created. It's called average for the station, average STA. So if you go in there, same folder structure. And now there is that pickled file. That's the station average, and also the plots folder where all of the plots that I just showed are stored. And you'll notice the name of this file, the name of this pickled file, it's actually encompassing the entire deployment time of the station, even though what is contained in this file does not represent the entire duration. It represents only 1 month of data. So it's better be consistent and actually use start and end when you want to do a station average to make sure that you're limiting your average to a certain time period. If you don't specify this start and end time, it's going to assume that all of the data represent the entire deployment time of the station. So that's why it's named this way. And if we go back here, you can rerun this example by specifying, say, 1 week of data. And I'm going to overwrite everything, not produce any figure. And this is going to run pretty quickly. And now you can look into average STA, this folder, and now I have a new file that actually reflects the 1 week of data that I included in the average. So it's going to look at this file to do the correction. It's actually going to look at both files you'll see later to do the correction. It's going to do one correction for each station average. And that depends on whether the earthquake happened during this time specified by the title. This is a little more detailed than probably is useful at this point. But we have done this quality control step. Now we're ready to calculate the transfer functions. And it's going to calculate all of the possible transfer function it finds in the daily averages as well as in the station averages. So it's create a called a transfer function noise object. And it's if there's only vertical and pressure component available for that station, it's only going to calculate this one. If there's only the seismic data available but no pressure, it's going to calculate only these. And this is determined automatically based on the content of the data folder for this station. And if both tilt and compliance, all of the 4 components are available, it's going to calculate all of these transfer functions. So Zn1, Z2 minus 1, which means that it has done 1 and then is doing the second. Zp and Zp minus 2, meaning it's doing the 2 horizontal components corrections first and then the pressure correction. And if you're doing this on a day noise object, so for a single day of noise, it's going to calculate these extra transfer functions. ZH is the transfer function between Z and the horizontal component rotated to maximum tilt. And this is only available for these daily averages because, as Helen was mentioning again, tilt direction changes over time. So calculating a whole station average of this particular tilt, maximum tilt component does not make much sense. So you'll get these transfer functions only when you apply them to a day-long noise data. So how are you going to do this? This is all done under the hood. You don't actually need to care about these details to run the code. You copy this, and there's also a bunch of options, scripts. If you go to transfer functions, again, the same kinds of options as we saw previously. If you just want to calculate the transfer functions over some time period, you can also do that start and end times. If you want to skip the daily averages, you can use this flag, skip the station average, so the skip clean option, and then just few figures again to create. So just running this one line. Oh, I'm not in the right folder. You notice I made a mistake. I'm in this average station folder. So I go back to the SIG folder, rerun this line, and it's calculating all of the possible transfer functions. And you see it's even calculating both station averages. It's finding all of these different station average files, and it's using them both to calculate the transfer functions, even though they actually contain the same thing. Well, actually, no, that's not true. One of them is for 1 week, and one of them is for the entire 30 days of data that's on the computer. So it did calculate all of the possible transfer functions. We could have limited this to some kind of time range. And if you look, there's another folder that was created. It's called TF for transfer function for that station. Has the same folder structure. Go in there, you have one transfer function per day, transfer function file per day, and also these station averages with their corresponding transfer functions. And I'm not going to do this again, but you can load them the same way in using Pickle as we saw previously. If you have questions about some of these high-level details, we're going to go over this in the Q&A. For now, it's not that important, but we forgot to produce a figure. So I'm just gonna rerun this. I need to overwrite everything again and create that figure TF, and it's gonna pop up on screen. There's actually maybe more than one. So here are the transfer functions between Z and P, between Z and 1, Z1, Z2 after 1 has been incorporated in this transfer function, ZP, and after 2 and 1 have been incorporated, Z and H and ZP and H. So all of the gray lines here represent 1 day of transfer function, and the black lines represent that station average. And now I think it has 2 black lines because there's 2 transfer functions for the station average that are being plotted. So that's it. And if you want to save them, again, make sure you have this save figure option specified, and same kind of folder structure. It's stored under a new plots folder, and you have this one plot that was created. Okay, so far what we've done is, well, download data that was done already. We've calculated all of the daily averages to flag the good and bad windows within that day. We made a daily average of those spectra, and also cleaned all of the spectra for flagging bad days during a certain time range, and created one single spectral average for that represents maybe that station or maybe 1 week of daily averages, and just calculated all of the possible transfer functions for these cases. The next step is to get the event information. So obviously you were interested about correcting your seismograms for specific events, and therefore you want to have the data on your computer the same way that these daily data, day-long SAC files have been pre-processed. So there is a nice script that does this. It's called ATaCR download event. The only drawback at this point is that it is not actually using the data in the data folder like these SAC files to extract the seismograms from that earthquake. It's actually re-downloading stuff from IRIS or from another repository. And therefore, this is something that will need to be changed in a future version of OBS tools. So this is a helper page. You see there are more options now, and these should be matched with the options that you used to download the day-long SAC data in this ATaCR download data. And currently there is no warning to tell you that you've been using different options. So this is also something that might be changed in the future. But right now it's not letting you know whether your options are the same as those that you've used to download the data. So you have to be careful, make sure you're using the same settings. So the ones that you want to make sure that they are consistent is the sampling rate, the units, the filter for deconvolving the instrument response. And now you have flags to find the earthquakes within the earthquake catalog, and geometry and minimum distance and maximum distance in terms of the great circle distance from the earthquake to the station to consider. There are some default values. You can change those by specifying those flags on the command line. And remember, when I went over the first step to download the data, I mentioned that I use a sampling rate of 1 Hertz. So for this tutorial, you will need to re-download the events using this line. But in addition, you have to be careful to add the sampling rate flag equals 1 to make sure that what's on your computer in this folder that you're seeing here on the terminal, the day-long files, are pre-processed the same way. So to do this, we have to specify sampling rate equals 1. And here you see the options are just trying to find all events with the minimum magnitude of 6.3, maximum magnitude of 6.7 within this time window of like March 8th and March 10th of 2012. So I already know there's an interesting earthquake within that time range, within this magnitude range. And so that's why I set these flags just for this tutorial. So if you just run this, it is actually downloading on the fly these seismograms and the pressure component as well. So you see here it's downloading seismic data, done, and it will remove the instrument response. So it's doing some pre-processing and some warning that the event stream object has been saved before the corrections have been done. Don't worry about this. All you need to know now is that your events are in the events folder, and they are, you have these SAC files. So if you want to look at them using your SAC software, you can. But the important file for OBS tools to have is this pickle file, because that's the one it's going to use for the next step when it's doing the noise removal. And this also is another shortcoming of this code, because you could use the SAC files in theory, but instead it's set up to use this pickle file. So bear with me and please contribute if you find that these shortcomings are too much for you. Well, help me fixing it. Okay, so we have our earthquake data. We're gonna go back to the SIG folder. And the final step is to clean the vertical component using all of our transfer functions that we have calculated already. And there's one script to do this again. It's called ATaCR correct event. If you look at the helper page, some information. Again, you can set some time window to search for specific event-related seismogram. So maybe you want to process only the first month of data from the earthquakes that the earthquake seismograms that you've saved. That's possible. You can also skip the daily transfer function calculations that have been done, or skip the station averages. So this is a bandwidth to plot the corrected seismogram. This is not used in the noise correction, it's just to plot the result at the end, and some flags for plotting figures. Again, plotting the raw data, plotting the clean data after the noise corrections have been done, and saving those. So if I go back to the tutorial page, I'm just going to run this one line, copy, paste, and it's going to produce that figure, which is showing the raw data. And you see the first one here is the vertical component, and there is an earthquake in there. Maybe for the trained eyes, you could probably make out something. If you look, maybe it's more obvious on the horizontal components when there's higher noise. These are the raw data that have not been filtered in the pressure component. But even just looking at raw data on the vertical, it's really hard to see that there's anything in there. And now OBS tools and ATaCR is going to remove all of the noise from all of the possible component combinations that you have stored. And it's using a filter to plot these on this figure. And you see all of the possible transfer functions that have been applied to the vertical component to produce a final cleaned vertical component data. It still looks a bit noisy, and you see the raw vertical component in the background in the gray and the cleaned signal in black. So if we only remove the component one and the horizontal component from the vertical, you get something here. You obviously clean a big chunk of data, but it's still fuzzy. If you then clean using the second horizontal after you've cleaned the first horizontal, now you see the Rayleigh wave a little better. It's still pretty noisy. And if you further remove the pressure component from the tilt corrected, from the horizontal component corrected vertical, now you get this nice Rayleigh wave. It still has a long coda, and that probably has to do with the bandwidth of the resampled data. So if you use a higher frequency corner when you're resampling, a higher sampling rate, for example, you might get rid of this. And what's interesting is you start to see the body waves arriving. So because, as Helen was saying, these shallow stations on the shelf, you can actually recover body waves because they're in the same noise bandwidth. And the ZH are not available for the cleaned station average. So this is, if you notice here, this is applying this transfer function for the station average and not for the daily averages. And so these two are not available for a station average. And if you just clean using the pressure component, you actually get something that's very similar to one that has been tilt corrected first and then compliance corrected. So for that particular station, for that earthquake, it doesn't seem to matter too much if you remove tilt, even though it does look better here. And then if you look at that particular day, on this is still, no, now I'm using the day-long files. The noise for that particular day when the earthquake happened, it has found that file. So it's day 069. And you can see now applying the noise corrections using the spectra for that particular day when the earthquake happened is also cleaning up your data really well. Obviously, you probably want to save those figures and using something like this. And it's going to just save the figures when it runs. Now, if you go into the events folder, you have the same folder structure, but now there's an additional corrected folder. These are still the raw seismograms, uncorrected. But now if you go into the corrected folder, you get all of these SAC files telling you which one has been corrected with which component, which transfer function essentially for that particular day-long noise information or the whole station information for that clean station average. And so you see there's 2 fewer components available for the station average than for the day-long average. So now you have your corrected SAC files. And this is pretty much it. This completes the demonstration of ATaCR. And there's all of these figures, the same ones essentially that I just showed, but this has been done using a higher sampling rate. And at this point, I think I'll stop sharing and maybe I'll take some questions if you have any questions about the way the code runs or more general questions about these noise corrections. And my assistants here can also help. And please consider contributing to this code. The more people that use it and contribute to it, the more stable it'll be and more versatile as well. But were there any questions in the chat, Steve or William, that require a response this time? Let's go with those first.
Yeah, sure. So Travis asked, when the archive, like when the recording goes up, how can people access it? Will they get a notification? Because he had internet trouble and he thinks he would like to watch back later.
Oh, you mean the whole session when it's going to be made public?
Yeah.
Yeah, so it's going to be made public at least to everyone that was in this session. And possibly also we're going to edit parts of it to make it public so that everybody can go over this tutorial on their own time, or anybody else in the community for that matter. But we'll see about that. But certainly for everybody who's been involved in this session, will have access to that.
Okay. Teresa asked, so she wanted to know how windows are flagged as good or bad. Some more details.
So this is based on the power spectral density, and I'm just gonna share my screen again. And I'll go to the tutorial part for, let's say, the daily spectral averages. And if we look at the figures, these are spectrograms. And what it's doing is calculating a power spectral density function for all of these different components. And it's looking at a certain band frequency range. So I think in this default setting, it's between 0.004 and 2 hertz. And actually, so you look at 2 hertz here and 0.004, and it will look at the way that these are different from the average. So you calculate the mean of all of the spectra and the standard deviation, and you look at which ones are further than 2 standard deviations away from the mean within this bandwidth, with this frequency band. And that's how those are flagged. And then it does an iterative process. When those are thrown away, then it does that again. Are there any more that we missed now that we can recalculate the mean, and so on. So that's how the quality control is done. It's the same that's done for a single day of data or for a whole average of over multiple days. I hope that answers the question.
Yeah, I had one more question from the chats come my way. So Martin asked, why not use the OBSPy inventory instead of station database?
Yeah, that's an excellent question. And the answer to that is because we started building these tools before, well, I guess that simultaneously as OBSPy was using inventory. So one way to improve this package is certainly to use the inventory from OBSPy. Although that STDB package, what it allows you to do is build your own database, and sometimes for private data that are not on Iris, for example, you might want still to use some station database that is not publicly available and will not be available through an inventory object unless you build it yourself again. And maybe the more advanced Python users can do that, but most people would find that difficult, I would say, and therefore that's where this STDB package comes from. And in the future, we want to integrate inventory objects with STDB, go back and forth between them, such that we can use inventory instead of the STDB package in those codes. But so far, this is a lot of work, so I'll leave that for maybe when we have time later.
That was it for questions that came in when you were doing the presentation, Pascal. I don't know. You can probably see now there's some more questions coming in the chat.
Yeah, I'm gonna have to go back a long way now to see what are the questions. If
I can just read them to you.
Sure. Maybe that's easier.
So Maria asks how to use this with a local data set with a different folder structure with this kind of code.
So the folder structure is built this way because it's easy to go between different stations, and that's just our way to do things. If you want to use a different folder structure, you probably will have to use the API and therefore dig more into the Python and maybe make your own scripts. But the scripts are built that way just to make it consistent. Now, if you want to use this with your own data, what you would need to do is make sure that it follows the same structure as the data folder that's on the Git repository. And if you put all of your pre-processed SAC files from your private data, let's say, in that kind of folder structure, then OBS tools will run with those, no problem. But you have to make sure that they have been pre-processed in a way that is similar to what is done in OBS tools. And after that, that folder structure should just continue as it is set up with, if you're using the scripts. Obviously, you can modify the scripts for your own application or play with the API, essentially calling these denoise objects through your own scripts. But that's more an advanced level of programming, let's say, than those scripts are meant for. But in the future, that's something we want to do is like, instead of downloading the data from a public archive, probably have a way to incorporate those from local data sets on your computer that you're not sharing. But again, this is something that's planned for the future.
Okay. Do we have time for more questions? There's one more, as far as I can tell.
Yeah, there's time, I think.
Okay. So Andrew asked, is there any danger that the Python and Matlab versions will diverge?
That's likely, I would say, because at some point, there's not the same people who are going to contribute to each, and there has to be some kind of say quality control between the two versions. There's going to be some oversight to make sure that those are consistent. Right now, those functions are almost mirror images of one another. The one thing that's most likely to diverge is, let's say, the packaging, the way the folder structure is built, and maybe you looking at local data sets and how to download data from the public repositories. But I'd say the main core routines will stay. And possibly there's something I want to look into is the way that good and bad windows are flagged. I think there's better ways to do a robust measurement to identify outliers than looking at 2x standard deviation, for example. But apart from that, and then probably I will coordinate with Helen and other people to do this simultaneously in the MATLAB version. So the core routines should stay the same, but the overall packaging and the way to run things is going to be different, because as people start to contribute to the code, it's hard to keep up the same versions between MATLAB and Python, obviously. Is there anything else? I see Brendan. So the flag windows in the tutorial was a window with real signal, and that's why it was anomalous, or was it anomalous due to some other issue? This is not specified here. It's just there is something wrong. It may be because there's an earthquake within that time window, and it's likely that the time window over which we saw that there was an earthquake, obviously the power spectral density is going to be different than all of the other noise windows. So that one would have been flagged as a bad window. But sometimes it's just because one component decides to behave weird, and therefore the component is going to be flagged as bad. But it does not discriminate between what kind of bad window these are. They're just considered all bad and ignored, because all we want is an average of those noise PSD functions. I see another question. Is there any reason for downsampling the transfer function before using it? So we're downsampling the raw data, not the transfer function. So if you're, the reason for this tutorial was to avoid essentially hogging resources on GitHub. So because I put all of these pre-downloaded data set on GitHub without any downsampling, it would have been a huge amount of data, very large files. And so I wanted to avoid that essentially, but I would recommend doing higher sampling rates as much as you can. But obviously that's limited by disk space. So the transfer function is going to use whatever frequency access is available from the raw data and the time windows that you've specified. And therefore, it's going to use all of the information. So the transfer function is not limited in bandwidth at all. It's actually using the entire frequency axis that's defined by your windows that you've decided. And obviously, the time windows need to be the same between your day-long files and the event file that you're downloading. Otherwise, that frequency axis will be different. So that's why you need to be careful with that. Was there any other outstanding question?
No, there's none in the chat, and I think
Emily, you have your hand raised, I see.
Yeah, feel free to use your mic too.
Yeah.
Cool. Okay, thanks. Yeah, I was just typing, and this is a really lazy question, but and it might have actually been covered already, so sorry if that's the case, but is there a quick way built into these tools to look at these kind of the results of, for example, tilt per day file? So maybe
you mean the tilt direction?
Yeah, something.
This is going to be contained in the I think in the daily averages.
Okay.
Actually, that's a really good question, actually, and then we'll test how I remember my code. So I'm just going to share my screen again quickly and go through one of these files. So I'm back in the SIG folder, and I think these should be in the Spectra folder. And if you want to look at what's contained, within these, you start a Python window, import pickle as pkl if you'd like. Sorry about that. And then see how many. I probably just want to use a random file here. So let's see, sp equals pkl.load open, let's say this one file, for example. Copy paste, read binary, and print sp as a dictionary. And I think this is where this would be located or not. If I can actually type keys here, I don't see tilt here. So it's not where they are located, apparently. So possibly in the average Spectra folder. Let's open one of these again. I'm going to use this one. And print as the keys, tilt is here. So now I can print sp.tilt, and that's the tilt direction for, actually it has calculated tilt over all of these days available. So
awesome. Okay, so it's there, and you just have to kind of grab it and plot it up how you want to. Yeah. Yeah,
exactly. And the information on the coherence between H1 and H2 is in there as well as the yeah. So you just have a little bit more digging to do, but this is all in there. And if you want to actually find out where these things are, I'm gonna again share my screen. This is all in the documentation. You have to look in the API documentation, the base classes and STA noise. It's showing all of the attributes and methods. So STA noise, the init function initializes it, and you see tilt is here. So these are the attributes of this STA noise object, and that's what I did. I accessed the tilt attribute of this STA noise object here in Python. So all the information should be there. That documentation may not be 100% accurate. So if you flag any mistake there, please let me know. Oh, and I wanted to show you also, I forgot to say this. If you do want to contribute, the easiest way, if you're not familiar with GitHub, is to raise an issue. So you go to the issues tab on top here, you raise a new issue, describe your problem or your suggestion as much as you can, as detailed as you can, submit it, and then we'll answer and possibly come up with a solution and implement that in the next iteration of OBS tools. Or the other solution is to fork this repository and then create a branch and then make a pull request if you're familiar with GitHub. That's a bit more advanced, but if you want to do that, certainly you're welcome to do that. Okay, I think I'm going to go back to the main room if there's no more question. So thank you everyone for sticking around. It's pretty late. So hopefully this will be useful for you, and don't hesitate to contribute. We're looking forward for feedback.
Thanks, Pascal. Appreciate it.
Yeah, no problem. Thanks, thanks, John. I think John was talking.
Yeah.
Thank you. All right, so I'm going to go back to the main room now. Bye, everyone.